Um, Hopefully you can all see the screen and hear me.
Yes.
So it's a pleasure to be here. I'm going to talk about order amidst disorder. And in particular, I'm going to concentrate on carbon-based nanodevices, ones that are regular, that you're familiar with, but also semi-regular ones, TADDY ones, and ones with atypical random disorder. Some of this work is related to my 2014 paper, but most of it is work that I've done in collaboration with Thomas Novotny, who's at Charles University in the Czech Republic. You can see we're not related because he spells his last name correctly. And it's in this archive paper. Well, it's a pleasure to be here talking to everyone, although I admit the organization of the conference is very nice, but I much preferred when I came to the conference in 2015, because then I could see sites such as this one, as well as to meet people face to face. So this is, of course, St. George with the dragon. And what I'm going to be talking about today also is quantum dragons. So let's talk about single wall carbon nanotubes. So here, for example, is a armchair single wall carbon nanotube. It's metallic, and you can actually purchase this from a number of different companies, depending on the purity you want. If you want 99% purity, it will cost you about $900 per milligram. And you can look at the lengths of these metallic nanotubes. What I want to concentrate on is the electron transmission in these metallic carbon-based devices. And in particular, I want to look at cases where transmission is equal to 1 for all energies, and we'll say more about that as we go along. But let's see what this looks like experimentally. So I could pull a number of different experimental groups apparatus up. What we have is a source and a drain electrode, and you lay your nanotube, metallic nanotube or metallic device across these. And they do some measurements, which are extremely difficult. Being a theorist, I can approximate this experimental device in this way. I have my nanotube, here an armchair nanotube, and I'm going to think of connecting it not to actual physical electrodes, but to semi-infinite electrodes that are 1 atom thick, and that those are connected off at plus and minus infinity to some macroscopic source and drain. So this is going to be the idealized situation that I'm going to study. We can also look at carbon-based devices in nanoribbons. Here's a Zigzag nanoribbon. This is an experimental view of the same thing. Here's my theorist view, and I want to study transmission, so I'm going to attach these semi-infinite thin leads. And actually, what I want to do is I want to go to the simplest model. So I'm just going to look at the hopping between the pi orbitals of my device, and also the on-site energies. And it'll be no surprise that a Zigzag nanoribbon can have transmission equal to 1 for all energies of the incoming electron in this model, and consequently in this experiment as well. Well, you get the transmission basically from solving the Schrodinger equation of your nanodevice plus the attached leads. And you can look at what happens if the transmission is equal to 1 by going to this 1985 paper of Bodeker, Emery, Landauer, and Pinnas. And this is basically Ohm's law, but now for your quantum system, where the current has to do with the chemical potentials of your source and drain sitting off at infinity. And what enters here is 1 minus the transmission. And you have an integral over energy. So if your transmission is equal to 1 for all energies, that means that 1 minus the transmission is 0, and you have 0 electrical resistance. So for metallic system, you have transmission equal to 1 for all energies, and you have 0 resistance. Although quantum is different, so you actually have to look at how you're going to do the measurement. It turns out that if you look at the inverse of the resistance, so if you look at the conductance, if I do a 2-probe measurement in the limit of transmission going to 1, goes to the quantum of conductance, which is twice the square of the charge of the electric charge divided by Planck's constant. On the other hand, if I do a 4-probe measurement, the electrical conductance goes to infinity, and that means the electrical resistance goes to 0. So it's kind of strange. On the same device, you can get different resistances depending on how you do the measurement. But what I want you to keep in mind is that if the transmission is equal to 1 for all energies, the electrical resistance is 0 in a 4-probe measurement. And even though this is strange, of course, quantum is right. So here's an experiment that tested that you get 2 different resistances depending on how you do the measurement of the same device. They did a ballistic device, so no scattering, and did a 4-probe measurement and a 2-probe measurement. And in the 2-probe measurement, this is what they measured for the resistance. It's basically the step functions for the quantum of conductance, just as you would expect. For the 4-probe measurement, they got a resistance of 0, just as you would expect for a 4-probe measurement. So again, if the transmission at all energies is equal to 1, we know the electrical resistance in a 4-probe measurement is 0. So I'm going to study the simplest model, the tight binding model. Basically think of the overlap of the pi orbitals. We'll have our on-site energies, which can be different at every site, and the hopping from one pi orbital to another. That's the T's. And I'm going to just constrain myself to nearest and next nearest neighbor type of interactions. We'll think of having m atoms in each slice. So these yellows are different slices, whether I have a regular lattice or a disordered graph, and I'll have little l different slices. So what we have in our model is basically a graph, such as the graph for graphene, plus our Hamiltonian, our single band tight binding Hamiltonian with its on-site energy and its hopping strength. And for graphene, this is the model I have, plus the attached leads. And the radii that I have is proportional to the on-site energies or to the hopping terms, except I can choose my 0 of energy wherever I want. Let me choose my 0 of energy to be the on-site energy of my uniform leads, and I'll color code those yellow. So graphene has transmission equal to 1, it's metallic. That's very nice, but I don't want to study just graphene. I want to study, again, a graph plus the same Hamiltonian with on-site energies and hopping, but I want to study a disordered graph like this. And if I put on my Hamiltonian, it's going to have this form. So I'm not going to have any translational invariance. So the question is, how do you analyze it? And I hope to convince you that this device actually has 0 electrical resistance. So again, the radii I color code the on-site energies and the hopping terms in my disordered Hamiltonian, which is living on my disordered graph. So I'm going to restrict myself to nearest and next nearest neighbor hopping, and I'm only going to look for cases of disorder where the transmission of the electrons coming in at all energies is equal to 1. And I'm going to do this by only correlating locally the disorder. And I'll say more about that as we go along. But first, let's talk about the leads. Because what we want to do is we need to attach leads to our device. So here is a disordered system. I have a lead coming down from the top, for example, and I'm going to have a uniform lead. I'll choose my energy for the uniform lead to be the on-site energy of 0. I'll choose my length scale of energy to be equal to 1 as the hopping strength in the lead. I can write down the dispersion relation, and I want to look for quantum dragons. I basically want to look for cases where the transmission at all energies is equal to 1. So I'll take my quantum device, I'll attach these 2 leads and calculate the transmission. as a function of energy, because that is what enters into the conductance and the resistance. So how do I calculate the transmission? Well, my Hamiltonian is very traditional. I'm going to use a traditional method to calculate the transmission. This is the non-equilibrium Green's function. And if we define these two constants, remember I've set the hopping in my lead to be 1. So this is 4 minus E squared, the energy of the incoming electron, square root of that. And sigma is this. I can introduce the self-energies, which are associated with the fact that I have an open quantum system, so I have leads attached to my device. These are the vectors that attach the left or the right lead to my device. I can then introduce the broadening function in the typical fashion, and then write down the Green's function, which is the Hamiltonian of my device subtracted from the energy of the incoming electron times identity matrix, and then subtracting the two self-energies. So with the Green's function, I can get the transmission in the normal fashion by just taking the trace of gamma for the left lead, the Green's function times gamma right for the right lead, times the permission of the Green's function. Take the trace of that, and in this case where I only have with one leads, I can actually write it this way. Since I have the Green's function, I can look at one more quantity, and that's going to be the local density of states. So at every site, I can look at the local density of states at a particular energy, and that's just equal to the diagonal elements of my Green's function once I take minus 1 over pi and the imaginary part of that. So I'm going to calculate both the transmission and the local density of states in a completely normal fashion. So now what I want to do is I want to look at, well, if I have a disordered system, here a typical disordered system, so it lives on this graph, and you can see the disorder in the on-site energies and the bonds and so on. If I look at the transmission as a function of energy, usually for most energies, the transmission is extremely small. But I don't want to look at such typical disorder. I want to look at atypical disorder. I only want to look in cases where the transmission of my electrons for all energies is equal to 1. So instead of this plot for transmission as a function of energy, I get this plot for transmission as a function of energy. At every energy, the transmission is equal to 1. So I'm going to study these quantum dragons. So let's look at the length scales in our problem. Well, we basically have 3 length scales that the experimentalists tell you because they've made the device. One is the length of the device, L. Another is the lattice spacing that they've used to construct the device. And they also are going to have some, say, static scattering centers in their device. So I can look at the typical distance between the scattering centers. So those are the 3 length scales that an experimentalist is going to give you for the device. But then when you measure the transmission, there's 2 more length scales that you have to be concerned with. One is was introduced by Marketson. It's basically the length of my device times the average transmission divided by 1 minus the average transmission. Here the average is basically an average over the different scattering centers. If I have a ballistic system, that's the elastic mean free path, how long the electron goes until it hits a different type of scattering region. And I also have to worry about the Anderson localization length. So a lot of people have studied transmission through nano devices, experimentally and theoretically. And there are 3 different regimes that people study. These are all well studied. One is the ballistic regime that has transmission equal to 1 for all energies. And that's because we have an ordered system. And therefore we can solve the ordered system in the ways that we know about. And you have transmission equal to 1 for all energies. The electrical resistance in a 4-probe measurement is 0. On the other hand, so this is what happens if your system is much smaller than the typical distance between scattering centers. On the other hand, If your system is much bigger than the typical distance between scattering centers, you have a diffusive regime where your electron is going to scatter a number of times before it gets from one end of your device to another. There, the transmission is small for almost all energies. And if you go to even longer devices, you can have your device longer than the Anderson localization length. So these three regimes are very well studied, and these are for ordered systems or systems with typical disorder. I don't want to study that. I want to study only metallic nanodevices, ones with transmission equal to 1, but ones that have atypical disorder that allow me to have transmission equal to 1. And I call those quantum dragons. So you have transmission equal to 1 for all energies. Consequently, you have 0 electrical resistance in 4 probe measurements. So here's an example of a quantum dragon for my 2014 paper. You can have strong disorder and yet have total transmission equal to 1. This is a device that only a theorist could love. So I'm going to look at atypical disorder that allows me to find a quantum dragon. So let me back up a little bit and have a quote from a Polish science fiction writer, Stanislaw Lem. He says, "Everyone knows that dragons don't exist." So let me tell you why physicists, including myself before 2014, did not believe that quantum dragons could exist. So let's look at the simple 1D case. 1D scattering, we have an electron with a particular energy, and we might have some resonant energy here. This is the transmission as a function of energy. And right at the end of resonant energy, you have transmission, say, close to 1. But that's not what I want for a quantum dragon. For a quantum dragon, I want transmission equal to 1 for all energies. And that's not going to happen in this one-dimensional system. Another example why physicists believe that quantum dragons shouldn't exist goes under the name of Anderson localization. If I have a one-dimensional system, then I know that with any type of disorder, I'm going to have all wave functions localized. So if my device is large enough, there's no wave function that goes from one end of the device to another. And consequently, what happens is the transmission is going to be extremely small for all energies. So let's go on with the quote from Stanislaw Lem. He says, "Everyone knows that dragons don't exist, but while this simplistic formulation may satisfy the layman, it does not satisfy for the scientific mind." So what we want to do is we want to basically find these atypical random systems. We want to calculate them. And the question is, how do we do that? Even if I tell you that quantum dragons exist, how are you going to go about finding them? Because we have an open quantum system. I've attached the leads with the reservoirs at plus or minus infinity. That means I have a very complicated, difficult system to calculate because it's an open quantum system. I want a large device, say 10 to the 23rd atoms. This is a complicated, disordered quantum device, making it, again, more difficult. So there's no translational invariance, there's no block function. How do you even look for a quantum dragon, even if you think one exists? You might say why I call them quantum dragons. We could say more in discussion, but it's basically because they're kind of quasi 1D, and you have to be lucky to find one because these are atypical types of disorder. So let's look at how we would analyze something which is ordered, like this zigzag nanoribbon. We know the transmission is equal to 1 for all energies. We have ballistic electron propagation because there's no disorder. And if I look at the local density of states, again, I get that from the diagonal elements of my Green's function. The local density of states is ordered. Basically, every site has the same value. So that's not surprising. But now I want to look at a disordered system like this that I showed you before, based on this disordered graph. I want to have the disorder such that I have a quantum dragon. I have transmission equal to 1 for all energies. But I'm going to have order amidst disorder. So I'm going to have order amidst disorder. I have a disordered device, but if I look at the local density of states, it's ordered. In other words, the local density of states at every site is exactly the same. So that's what I mean by order amidst disorder. So how do we go about finding order amidst disorder and these quantum dragons? Well, we start with a hard problem for our device. We attach our leads. And now what I want to do is I want to look for a similarity transformation in Hilbert space of my Hamiltonian that is going to rotate to different bases in Hilbert space. And in that new basis, I'm going to have a one-dimensional system which is connected to the incoming and outgoing leads, plus some other degrees of freedom that are disconnected from the leads. So I'm only going to look at problems where I can actually write down the similarity transformation to map exactly onto the transmission of this one-dimensional system. That makes it easier to calculate the transmission, for example. But in some cases where my disorder is of the right type and tuned the right way, when I perform this similarity transformation, I don't get a disordered 1D wire, which would have Anderson localization and so on, but I get a uniform wire. And because now I have a completely uniform wire, I get transmission equal to 1 for all energies. So that means I've found when I do the similarity transformation, if in the new bases in Hilbert space, I have this uniform wire, I basically have a quantum dragon. I have transmission equal to 1 for all energies. So this is the first figure in the 2020 archive paper. Again, here's my Hamiltonian. I start with a disordered, here's Zigzag nanoribbon. I'm now going to correlate the disorder just locally. I'll perform the similarity transformation, and this device in physical space in this new basis looks like this. I have a disconnected part of my Hamiltonian, and I have a uniform wire. And I can do this, I can find this quantum dragon having only locally correlated the disorder and still have transmission equal to 1 for all energies. So they will show order amidst disorder. And furthermore, I'm only locally correlating the disorder. And I'll talk about regular, semi-regular, TADDI, and atypical random systems. So how do you actually find these quantum dragons? Well, you can look at the form of the matrix that you have that enters the Green's function. It's a block tridiagonal matrix like this, where the A's are for each slice and the B's take you from one slice to another. And then what I want to do is I want to write down a similarity transformation, and I'll write down a similarity transformation which is block diagonal. And all I'm doing is changing the bases, but nevertheless I can go from the physical space to the new bases where I have a one-dimensional system. And to be able to do that, really what I require is that each of these blocks in my Green's function have exactly this one common eigenvector. So one common eigenvector allows me to essentially block diagonalize every block in my block tridiagonal matrix, as well as I have to attach my leads in just the right way. So in essence, it turns into a set of 7 matrix equations you have to be able to solve. But one way of solving these are to insist that every matrix in your block tridiagonal matrix has one common eigenvector. That means these matrices don't commute. In fact, the slices don't even have to be the same size, so the matrices don't have to be square. But nevertheless, if you can solve these 7 sets of equations, you can say that the transmission of your large device is exactly equal to the transmission of a one-dimensional system. And if the disorder is just right, so you get a uniform wire in this rotated basis, you have a quantum dragon transmission equal to 1 for all energies. And in 2014, I studied only axial symmetric systems, such as this beta lattice, and found that you can have disordered beta lattices and have perfect transmission. And that allows you to calculate, and even without perfect transmission, you can calculate exactly the transmission as a function of energy with no approximations in the cases where the disorder allows you to do this similarity transformation. So for example, for this beta lattice with a branching ratio of 3 and 100 slices, the red curve is exactly the transmission that you get for this number of sites, which is about 10 to the 47 sites. So I'm doing that transmission exactly. Just to give you an idea, the number of nucleons in all the water on Earth is about 10 to the 47. So in 2014, I had a menagerie of axial symmetric quantum dragons, such as these, which included the armchair nanotube, and ones that only a theorist could find interesting. So the breakthrough that we made, and that's in our 2020 archive, is basically we only have to correlate locally the disorder to be able to, and still be able to have a similarity transformation that in this rotated basis in Hilbert space has a uniform 1D wire. In other words, we can find a quantum dragon by only locally correlating the disorder. And in particular for this case, where if I look at all the bonds that are horizontal have the strength 1, the same strength as in my leads, then for any of the vertical bonds, I can make them whatever value I want, as long as I make the on-site energies of the two sites that that bond is connected to exactly the same. So that's the locally correlated disorder I'm going to have. And if I do that, I end up with perfect transmission at all energies. I end up with a quantum dragon. So here I've color-coded and size-coded the on-site energies, and you can have a very complicated disordered device, but if you rotate it in Hilbert space, you end up with a uniform system. So this allows extensive disorder. I can make the strength of this hopping as large as I want, and as long as I locally correlate, in this case, the on-site energies, I have a quantum dragon. So again, what I need is I need a common eigenvector. And for this particular case of a zigzag nanoribbon, that turns out to be for every bond, every vertical bond, I just have to satisfy this matrix equation. So I can make T as large as I want, provided the associated epsilons are the correct value. So what I mean by extensive is I can make this vertical bond as large or as weak as I want for the hopping, as long as at the same time I'm changing the on-site energy. In fact, I can even cut this vertical bond, provided I set my on-site energy to be 0. So that allows me to do cuts along this nanoribbon. And still I have a quantum dragon, still I have transmission equal to 1 for all energies. So let's see how this works. So if I look at a uniform system, so here's a zigzag nanoribbon, you won't be surprised that when I do this analysis, in other words, I do this rotation in Hilbert space, what I see is I get a uniform wire attached to these uniform leads, plus some other degrees of freedom that are just hanging around, but they're not attached to the wire, and therefore they do not affect the transmission. If I have a typically disordered case, so here I have some typical disorder, and do the same unitary transformation in Hilbert space, basically I end up with everything connected And I can do this brute force, I can do that brute force, but I haven't learned anything. Now, if I look at atypical disorder, on the other hand, so if I have disorder like this, then if it's atypical disorder and I have a common eigenvector for the matrices that enter the block tridiagonal matrix of the Green's function, in my rotated bases, I get this picture. Again, I get some disconnected degrees of freedom. They're disconnected from the lead, so they do not affect the transmission. I have a uniform wire here, so I get transmission equal to 1 for all energies. And now if I add a little bit of extra disorder to this atypical quantum dragon system, I can get something that's nearly a quantum dragon. So that's a quantum dragon. I can get nearly a quantum dragon by adding just a little bit more disorder, which means that these degrees of freedom down here are weakly connected to what's going on in this wire in the rotated bases. So let me tell you more about order of mist disorder. Let me show you another example. So in this case, we have a zigzag nanoribbon that I've done some cuts with. I've, say, printed an X here. I have lots of disorder in my system. If I calculate the local density of states by calculating the Green's function and looking at the imaginary part of the Green's function, what you find is that the local density of states has exactly the same value at every site. In other words, my physical device is very disordered, but the local density of states is very ordered. In fact, for every site, it has this form, 1 over pi, the number of atoms I have in a slice, and divided by the square root of 4 minus e squared. So I have a disordered system. I have order here amidst disorder. I can also look at the bond currents, again, by using my Green's function, and it has this form. You can see how the current comes in and splits up into the various currents. So that's order amidst disorder, and these quantum dragons are going to have that. But now what happens if I am only close to a quantum dragon? Let's study that. Well, what we know is if we had a quantum dragon, the transmission would be 1 for all energies. But as soon as these other degrees of freedom are interacting with my uniform wire, I get phanoresonances. And in particular, the transmission is going to go all the way down to 0 from 1. So I have something that looks very much like a singularity. It actually has this form. And if I add a little bit more extra disorder on top of a quantum dragon, I will go from the red curve and then to the black curve and then to the blue curve. So the location where it goes down to 0, in all 3 cases, it goes down to 0. The location it goes down to 0 is different. So it's going to be moving around compared to where one of the eigenvalues of my quantum dragon Hamiltonian is. And basically, it's also going to widen. So to understand what happens for nearly a quantum dragon, we have to take into account these phanoresonances. And it's going to be different, and we're going to analyze it differently depending on whether we are near one phanoresonance or near many phanoresonances. So this is 1 minus the average transmission for a particular quantum dragon. And here I'm showing 3 energies in the 3 different colors and plotting symbols. And this is delta is the added uncorrelated disorder, on-site disorder that I've added to my quantum dragon. And you can see if I just add a little bit of uncorrelated disorder to a quantum dragon, I have 1 minus the average transmission goes as delta squared. Then there's some crossover, which occurs in different places at different energies. And then it again becomes proportional to delta squared. And that's because I have 2 different regions. This region where I'm near 1 phanoresonance for just a little bit of disorder. And if I have a little bit more of disorder, I can be close to and affected by many phanoresonances. So we analyze both of those cases. So let's look first at the case where we are near many phanoresonances. Then here's the quantum dragon transmission. I add a little bit of extra disorder, that's the red, a little bit more, that's a black, and more, it's a blue. And when we analyzed that, we actually found that the average transmission as a function of energy should have this form, where we have the density of states of our Hamiltonian without the disorder entering. And I can actually write that in a scaling form, which is this. And all of these points here collapse onto each other. And furthermore, they should collapse onto the density of states I get for these type of quantum dragons, and that's the green. So with no adjustable parameters, we have very nice scaling when you are nearly a quantum dragon in this regime where you're near many Fano resonances. In the case where you are near one Fano resonance, you have to analyze the disorder by using a different type of perturbation theory. And what we find is that the average transmission has this form. It's actually universal. It depends only on the strength of the extra disorder, on the energy of the electron, on the length, number of slices, and the number of atoms in a slice that you have. And if I plot this a different way in terms of scaling, these should all be equal to 1. So here I have lots of different types of devices with lots of different quantum dragons. I throw on just a little bit of extra disorder, and all of these scale as we expect. They scale with its universal parameter of 1 until things cross over, because I'm now affected by more than one Fano resonance. So the next question is, are quantum dragons buildable? So I have a couple of minutes. Let me do that. Here's the type of experiment that people have done for transmission for nanotubes. But people have also done partially unzipped single wall carbon nanotubes. So here's one picture of that. Here's the graph that they had in their experimental paper. I'm going to do exactly the same thing. I can partially unzip a single wall carbon nanotube, and yet I can have transmission equal to 1 if I do it correctly. Here's another experimental paper where they used partially unzipped single wall carbon nanotubes here for catalysis. But the prediction that I'm making is that when you partially unzip these carbon nanotubes, they are metallic, even though you have scattering because you've gone from a tube to a ribbon. So these are quantum dragons. And furthermore, I can, instead of cutting one place, I can cut 2 places and still have a quantum dragon. Again, now I'm going to show you all kinds of things based on carbon. So I just have a 2D hexagonal graph, and I'm going to keep my hopping parameters and on-site energies the same as if I were using a zigzag nanoribbon. So I can have this partially unzipped nanotube. I can have this nanoribbon with some holes in it. I can do other things. I can take this nanoribbon and cut a hole in it and then twist the 2 slices, put them back together. I get a quantum dragon, which is a Mobius dragon. So I have a Mobius a strip type of carbon-based device. I can do more complicated things, such as this or this, in terms of cutting holes in it and doing other operations I'll tell you about, to be able to still have a metallic carbon-based nanodevice. Here's another one. I think I used this one in my abstract. You can see you can have a very complicated quantum dragon. It's going to show order amidst disorder, even though you have a disordered graph and a disordered system. If you look at the local density of states, it's the same at every site. So the proper operations that we can do and still have a quantum dragon is we can do the printing, like I showed you in terms of the colored ribbon. You can do cutting or unzipping, which I've talked about. You can also do sewing, so I can take this ribbon and essentially sew the ends if I do it correctly. I'll still have a quantum dragon. I can do twisting, even adding a phase factor because the pi bonds, the plus and minus, go to minus and plus. So I can do the twisting like in the Mobius case. I can do braiding, whereas if I cut a bunch of strips, I can braid them together, or I can reattach them in different ways. I can move and add and remove some bonds. And if I do all of those or any combination of those, I still have transmission equal to 1 for all energies. I still have a metallic device, and I still have a quantum dragon. So here's a regular carbon-based device. Here's my Mobius strip, which is semi-regular. Here I have a tatty device. Here's something which is even tattier, and here's the tattiest of them all. But the important thing is all of these devices are based on the parameters that you have for carbon. They're analyzed in exactly the same way from the tattiest device to the regular device. And these are all metallic. So in summary, since I'm out of time, I hope I've convinced you, first of all, that quantum dragons exist, that the total transmission of electrons when you attach proper leads is equal to 1 for all energies of the incoming electron. So here's an example of a quantum dragon. You can have strong scattering possible, and still that strong scattering is such that the coherent electron transmission is equal to 1 for all energies. And you only have to locally correlate the disorder. So and furthermore, we looked at nearly quantum dragons and talked about how to scale for the cases of Hamiltonians where it's not a quantum dragon, it's just close to a quantum dragon. All of these showed order amidst disorder. You have a very disordered nanodevice with a uniform local density of states, and these can all be carbon-based devices. So with that, I will thank you and take any questions.